So I'm going to talk about joint work with Tom Hutchcroft, where we studied the geometry of the four-dimensional uniform spanning tree. So I'm going to start the talk by giving a little bit of background, fixing notation, and stating our results. And then I'm going to, in the second part of the talk, I'm going to explain some of the ideas behind the proofs. So if G is a finite connected graph, B is the set of vertices, and E is the set of edges, and G is called a tree if it is connected and it contains no cycles. And what is a spanning tree of the graph G? It's a subgraph of G, which is a tree, and it spans the whole graph, which means that it has vertex set V, the same vertex set as G, and it has no cycles. Okay, so if we have a finite connected graph G, then we can denote by calligraphic T the set of all spanning trees of G. This is going to be a finite set. And as probabilities, we like to pick things at random, so we can pick one spanning tree from this collection T uniformly at random. So we give all trees the same probability. And the tree we pick, we call it a uniform spanning tree, and I will abbreviate it as USD. So in this picture, this is a simulation by Sam Watson, and you see a portion of the uniform spanning tree of Z2. I haven't defined yet what we mean by uniform spanning tree of an infinite graph, but one way to think of it is as the uniform spanning tree of the box that you see here. Okay, so you may be surprised to hear that the study of spanning trees goes all the way back to the 1850s, and in particular to the work of Kirchhoff, that everybody knows about his foundational work on electrical networks. So this is the first page of his paper, which is in German, and in this paper, he developed a set of rules that formalize that current and energy are conserved in electrical circuits. And he was the first one to establish a connection between uniform spanning trees and effective resistance. So what he proved is that the effective resistance of an edge is equal to the number of spanning trees that contain the edge divided by the total number of spanning trees. So this ratio here is the probability that the edge E is contained in a uniform spanning tree. And the paper is only 8 pages long, and he proved a lot of amazing things. And one of them was the matrix tree theorem, which gives a way to count the number of spanning trees of a graph by looking at the Laplacian of the graph. So as I said before, Kirchhoff's motivation came from the electrical network point of view. And it was not at all probabilistic, but his insight has been fruitful in both directions. And actually using electrical networks has been a very important tool in the study of the geometry of large uniform spanning trees. So now I defined what we mean by uniform spanning tree of a finite connected graph. Now let me give you a little bit of motivation why we care to study this object. So first of all, picking a uniform spanning tree is an essential component in a lot of randomized algorithms in computer science. It is connected to other models in statistical physics, like the random cluster model. I'm not going to go into that in more detail. And as I already said, there are a lot of connections between uniform spanning trees and electrical networks. And as we'll see later, it's also connected to random walks and what I will define later, the loop-erased random walk. And lastly, Odette Schramm was studying the scaling limit of the uniform spanning tree, and this led him to develop his beautiful theory of SLE, Schramm-Levner evolutions, that are either the proven or conjectural scaling limits of conformal invariant processes on the plane. And here I just want to show you a beautiful picture. This is due to us lions. And here you see a uniform spanning tree of the box, which is traced by the piano curve. And in the scaling limit, this converges to an SLE8. And the different colors correspond to the different times at which the piano curve traces the uniform spanning tree. So this is in 2 dimensions, and my talk is going to be about higher dimensions. I just want to show you this picture. So, okay, is connected graph enough to guarantee that this one? Yeah, so just take all the vertices of the graph and then put the minimal number of edges that make it connected, and this gives you a spanning tree. And then you just consider the collection of all spanning trees. And because the graph is finite, it's a finite collection, so this probability measure is well defined. Okay, so now I would like to tell you a little bit about sampling algorithms. So suppose that we have a finite connected graph G, and we would like to sample a uniform spanning tree of G. So there are various algorithms. The first one goes back to the matrix tree theorem, because as I said before, this gives you a way to count the uniform spanning trees of a graph. So in particular, it gives you a way of generating a uniform spanning tree. Another algorithm is due to David Wilson, and this uses loop erased random walks, and I'm going to talk about this in a little bit. And another algorithm is due to Aldous and Broder, and they both acknowledge discussions with Perla diaconis, and I'm also going to talk about this later, and extensions to the infinite setting. Okay, so in order to talk about Wilson's algorithm, let me first define what we mean by a loop erased random walk. So if gamma is a finite path of vertices in G, I want to define the loop erasure procedure. So the way I'm going to erase loops is I'm going to do this. I will erase them in the chronological order in which they appear until there are no more loops left. So suppose that this is gamma, then I'm going to delete, this is the first loop, that's the second one, third one, fourth one. And so what we get is this path. So that's what we mean by the loop erasure of a finite path. You just remove the loops as they appear. And now if you have a finite simple random walk path, so you just run a simple random walk for a finite time, you can apply the same procedure to this path, and this yields what we call a loop erased random walk. Now, if you are in a transient dimension, this procedure is also well defined. So you can loop erase a 3-dimensional simple random walk path or a 4-dimensional, because it will visit every vertex a finite number of times. But if you want to do this in 2 dimensions, for instance, when the walk is recurrent, one has to define it appropriately. And so in 2 dimensions, I just want to show you this picture. If you take a loop erased random walk on Z2 and say you wait until the first time that you exit a ball of radius n, and then you rescale it, then this is going to converge to what is known as an SLE2 curve. Okay. So now that I defined what we mean by the loop erasure of a path, I can describe Wilson's algorithm. So we have a finite graph G, and we designate some vertex R to be the root vertex. So we fix it, and then we order the remaining vertices of the graph. We just pick an arbitrary ordering, but we just stick with it. And now the way the algorithm works is that we start a simple random walk path from the first vertex in this ordering. So this is V1. And we run the simple random walk until the first time that it hits the root vertex. So if this is V1, then we run it and we stop it when it hits R. And then we erase loops from this path. So we're just going to get this path. Okay. And then we start a simple random walk from the second vertex in the ordering, from V2, and we run it until the first time that it hits the first path that we have created. So if V2 is already on the path, then we do nothing. Otherwise, we start a random walk and we run it until it hits the path. And then again, we erase loops. And we keep going until we exhaust all the vertices of V minus R. And so in the end, it's obvious that what we got is a spanning tree, because by construction, we haven't created any cycles. But what is remarkable is that the distribution that we get is that of a uniform spanning tree. And this is what David Wilson proved. And what is amazing is that the distribution does not depend on the choice of the root vertex or the ordering of V minus R. Okay, so this is Wilson's algorithm. So I defined it in the finite case, but it's clear that one can generalize it for an infinite graph, which is recurrent. So let's take Z2. We can again fix 0 to be our root vertex, and we order the remaining vertices. And now we start a similar walk from the first vertex in the ordering and we run it until it hits 0. And it will definitely hit 0 because the walk is recurrent. So this is well defined. We erase loops from this path. And then we start a similar walk from the next vertex in the ordering and so on until it hits the previous path. We erase loops and we keep going. And so because the random walk is recurrent, this is well defined. And so this is going to produce a spanning tree of Z2. And this is the picture I showed earlier. And the reason why we call it the uniform spanning tree of Z2 is because if we restrict to a large box around 0, then this object will look very similar to what the uniform spanning tree of the box would look like. I'm just looking at the chart. Okay, I guess there is no question. Okay, okay, so this is how to generate a uniform spanning tree of an infinite graph, which is recurrent. And now, how can we generate a uniform spanning tree of a transient graph? Well, we cannot use the algorithm that I just described, but the canonical way is just to take a finite exhaustion of the graph. So suppose that we are on ZD, we can consider the boxes of side length 2n around 0. And we know how to define the uniform spanning tree measure on these boxes because these are just finite graphs. And then it's not hard to show using electrical network theory that the sequence μn converges weakly to a limiting measure. And moreover, the limiting measure is independent of the choice of exhaustion that we picked. And the limiting measure is what we call the uniform spanning forest measure on ZD. The reason we call it forest is because a priori we don't know whether it's connected, and but we know that it is supported on graphs that contain no cycles, so it's definitely forest. And the first question that we want to ask is actually whether it is connected. And this was answered by Robin P. Mantle in 1991, who showed that in dimensions below 4, the uniform spanning tree contains only one tree with probability 1, and in higher dimensions, 5 and higher, it consists of infinitely many trees with probability 1. And so this phase transition at dimension 4 for the connectivity is what makes dimension 4 be the critical dimension for this model. And I'll come back to this in a little bit. Okay, so now we know that in dimension 4, we have only one tree. In high dimensions, we have infinitely many trees. And what we'd like to understand now better is the geometry of every tree of the uniform spanning forest. So I'm going to introduce this notion of k-endedness. So if we have an infinite tree, we call it k-ended if starting from every vertex of the tree, there are exactly k distinct infinite simple paths that start from this vertex. So the integers z is a two-ended graph, is a two-ended tree, while the natural numbers is one-ended. So now the question is whether the trees of the uniform spanning forest are one-ended or not. And so what Pimentel proved is that in the same paper as before, is that in dimensions 2, 3, and 4, all trees are, so it is a single tree because it's connected, so the tree is one-ended. And in dimensions 5 and higher, he proved that they are at most two-ended. And then Benjamini, Lyons, Spence, and Schramm, 10 years later, showed that actually all trees, so that in all dimensions, all trees are always one-ended with probability 1. And of course, here we need d greater than or equal to 2, because in dimension 1, it's the whole of z, so it is two-ended. So is the definition of one-endedness clear? So let me just repeat. A tree is called one-ended if starting from every vertex, there exists exactly one infinite simple path that starts from the vertex. So you could have this picture, and this one here is the infinite path, while this part here is finite. So starting from 0, there is a unique infinite path, and everything else is finite. Okay, so now, because of this theorem, we know that all trees are one-ended with probability 1. And now the next step is to quantify this one-endedness. So in order to do that, I'm going to define the past of 0 in the following way. So let me just draw. So let's say that 0 is here. And this is the tree of 0. So we know that this tree is one-ended. So starting from 0, this is going to be the unique infinite path. And now the past of 0 is going to be the finite component that is disconnected from infinity when we delete 0. So it's this part here. So this is the past of 0. So we know that this is a finite component, and we are interested in quantifying the size of this component. So is the definition of the past clear? Okay. Okay. So
Can I jump in with a question?
Sorry.
I wanted to ask for the clarification about the definition of like one-ended versus two-ended. I don't quite get it yet.
Okay, so one-ended means, so the integer z is two-ended because from every vertex, so if these are the integers, 0, 1, and so on, then from every vertex, there exist two paths to infinity, from here and from there. While if you just take the natural number, so just this line, then from every vertex, there exists only one path to infinity.
I see. And what happens with like Z2 with the plane grid?
So this is one-ended. Sorry. Infinite-ended. I'm sorry.
That's what I was wondering. Yes. Okay. Thank you.
Yeah. Thanks. Sorry. Okay. So what Tom Hutchcroft proved for dimensions 5 and higher is that so here we are considering the past of 0. And sorry, so you said for, I'm sorry, I got confused. So you said for Z2, it is again one-ended, but if you take a k-regular tree, for instance, then this is going to be infinitely ended because you can have infinite many paths going to infinity. So, but Another way to think of one-endedness or k-endedness is that if you take any finite set, then you want to disconnect it into k. So it is k-ended if taking any finite set, then it disconnects the graph into k disjoint components. Okay, so for dimension 5 and higher, Tom proved that the path of 0, the probability that the path of 0 contains a path of length n is up to constants 1 over n. And the probability that the path of 0 reaches the ball of radius n, the boundary of the ball of radius n, grows like 1 over n squared. And the probability that the path of 0 is at least n grows like 1 over square root of n. Let me just say what I mean by the symbol. I mean that there exist universal constants, so that in the C1 and C2, so that for every n, this probability is, say, upper bounded by C1 times 1 over n and lower bounded by C2 times 1 over n, and similarly for the other quantities. So, what he proved in high dimensions, actually he proved this for ZD for d greater than or equal to 5, but also for more general graphs satisfying, for more general transitive graphs satisfying a quintic volume graph expansion. So as you see here, then these probabilities do not depend on dimension. So this is a mean field setting that the path of 0 in this case does not depend on the dimension. And what we were interested in was to understand what happens in dimension 4, which, as I said before, is the critical dimension for this model. And usually in the critical dimension, one expects these sort of probabilities to behave like in the mean field setting, but with logarithmic corrections. And so what we were interested in was to find the exponents that appear in the logarithms. And so what we're able to prove is that the probability that the path of 0 contains a path of length n is in 4 dimensions asymptotic to 1 over n, and the logarithmic correction is log n to 1/3. For the second probability, which in 5 dimensions was growing like 1 over n squared, we have the log n to the 2/3, and we have a small error of little of 1 here. So what this means is that for every epsilon, there exists a constant C epsilon, so that this is upper bounded by C epsilon times log n to the log 2/3 plus epsilon, and so on, and the same for lower bound. And for the size of the path, we proved that the correction is log n to 1/6. Let me just say that the lower bound here, in the second case, we don't need the little of 1 term. This is only in the upper bound, and I just want to say that the lower bound is the easy direction of this theorem. The delicate thing is to prove the upper bound. So what I will do in the rest of the talk is I would like to explain some of the ideas behind the proof of just the first bound, because this is the most important bound in order to obtain also the other two. And I'm only going to explain, I'm going to give an almost complete proof of the lower bound, that this probability is at least log n to 1/3 over n. And I'll just, and I will not prove the upper bound, which is the hardest direction. Okay, so in order to do that, so before I defined, I described Wilson's algorithm for generating a uniform spanning tree of a finite connected graph. So now I would like to describe another algorithm due to Aldous-Broder, again for a finite graph. So suppose that this is our finite graph, and we fix this vertex in the center that we call O. Now I'm going to start a random walk from O, from the center, and I'm going to run it until the cover time. So the cover time is the first time that the random walk has visited every vertex of the graph at least once. Okay, so and for every vertex that we visit, which is not the starting vertex O, we're going to color the edge that was used when we crossed, when we visited this vertex for the first time. We're going to color it green. So let me do it here. So we start from the center, then we went down. It's the first time that we visited, so we paint it green. We went up, went there, we went down, we do nothing, we do nothing. We went there, then went back. Now we went to the center, we do nothing for the starting vertex. And now we went up, again, we don't color this edge green because this vertex had already been visited before. And now we went down there, and now every vertex has been visited. So that's the cover time. And we have this collection of, this collection of green edges. And by the way that I described the algorithm, the collection of all these edges gives a spanning tree, because by construction, we didn't create any cycles. But what is less obvious is that the distribution of the spanning tree is the correct one. So it's again a uniform spanning tree on the graph. And this was proved by Aldous and Broder, and they both acknowledged discussions with Diaconis, because actually, in order to prove it, they use a Markov chain, which was introduced by Diaconis before, which is a Markov chain on the space of rooted trees. So you have a tree with a designated root, and then it's Markov chain which moves the root to a neighbor. And so this gives you, and then you add this edge, and then you have to delete an edge. So it's a Markov chain on the space of rooted trees. And then what they prove is that the uniform spanning tree measure is the invariant measure on the tree component. And so then they prove that this algorithm actually gives the invariant distribution of that Markov chain, so it has to be the uniform spanning tree measure. Okay, so all we need is, and actually the proof is like 1 or 2 pages long. Okay, so we have a finite graph. What we do is we run a random walk until the cover time, and then for every vertex apart from the starting vertex, we keep the edge that was traversed at the first time when we visited the vertex. And we keep all of these edges, and this gives, and all these edges is a spanning tree, and it has the correct distribution. Okay, so again, it's clear how to generalize this algorithm to an infinite recurrent graph, because every vertex will, because a walk will visit every vertex with probability 1. So we just run the walk forever, it will visit every vertex, and then for every vertex, we just keep the first edge that was crossed when visited the vertex. And this gives a uniform spanning tree of the recurrent graph. It has the same distribution as the algorithm I described earlier. So this is a way to generate a uniform spanning tree of a finite connected graph. And I explained how to generalize to a recurrent graph, but it's not clear how to generalize to a transient graph for the same reason as before, because running the walk forever is not going to visit every vertex. And this is what Hutchcroft did in his PhD thesis. So he generalized the Aldous-Broder algorithm to the infinite transient setting. So let me describe how he did that. So as I said before, the issue is that a single walk will not visit every vertex. So his idea was to replace the single walk by a Poissonian cloud of random walks. And this is what is called the random interlacements process, which was introduced by Sneedman in the early 2000s, I think. And he used it in order to describe the trace of a simple random walk in transient dimensions and disconnections of the cylinder by simple random walk. So what is this process? So as I said before, it's a Poisson process. So it's a Poisson process of bi-infinite random walk trajectories that arrive in time. So I don't want to go into detail and describe the whole intensity measure of this Poisson process, because when you have a Poisson process, in order to describe it, you need to write down the intensity measure. So I'm not going to write that because this would take some time, but I'm just going to explain the important property of random interlacements that we're going to use. So, okay, so as I said, random interlacements is a Poisson process. So you have bi-infinite random walk trajectories that arrive in time. And so it's a Poisson process on the space of trajectories times time. And in order to define the intensity for the time component, we just take the Lebesgue measure. And one has to define the intensity for the bi-infinite trajectories. But the important property that we use is what I have here. So let's suppose that we have a finite set K. And we want to ask, what is the probability? So we have these random walk trajectories that arrive in time. And want to know what is the probability that the set K has not been hit by any of these trajectories in the time interval from 0 up to t.
Sorry, Perla, can I ask a question?
Yes,
Very
yeah.
naive. What we might have said, but what do you mean by transient graph?
Oh, sorry, yeah, I didn't say. So I just mean that simple random walk on the graph is transient.
Okay.
So it with positive probability that escapes to infinity.
Sure, thank you.
It never comes back to the starting place. So yeah, so so what I will be interested in is just Z4, but Hutchcroft's generalization of the Aldous-Broder algorithm works for any transient graph. So you just have an infinite transient graph, and then you have these bi-infinite random walk trajectories that arrive in time. And then the important property is that the probability that this set K here has not been hit by these trajectories that I have drawn here by time t is e to the minus t times the capacity of K. And I will explain what the capacity of K is. So if you have a finite set K, then the capacity of K is defined to be the sum over all points of K in K of the probability starting from X that you never come back to K. So this is for a simple random walk that starts from K and we want it to avoid K forever. So that's the capacity of K. You may have seen it in the continuum setting. So this is the discrete analog of what is known as the Newtonian capacity. So in the continuum setting in RD, if we take A, which is a compact subset of RD, the capacity is defined as the inverse of this infimum. So here the infimum is taken over all probability measures mu that are supported on A, and this G here is the green kernel for Brownian motion. And one has exactly the same variational characterization in the finite setting, where G now is going to be the green kernel of random walk, which is the expected number of visits to Y when you start from X and you run your walk forever. So that's why it's important that the walk is transient, because this is a well-defined quantity, GXY. So, so that's the definition of capacity. And as I said, one can also write it in this form. One can prove that these two definitions are equivalent, where G now is the green kernel of simple random walk. And so, okay, so what I've done so far, So what I've done so far is I described the Aldous-Broder algorithm in the finite setting. And now I'm trying to explain how to generalize this in the infinite transient setting. And the first thing I did is to define the random interlacements process. So we have these random walk trajectories that arrive in time, which it's a Poisson process of a certain intensity, and it satisfies these. And now I have to explain how to generalize the Aldous-Broder algorithm in this setup. So I will explain more on the next slide. So the idea is, like we're doing before, when we have just one walk, for every vertex, we're taking the edge that was traversed when this vertex was visited for the first time by the walk. Now we don't have one walk, we have a Poissonian cloud of walks. So for every vertex, we look at the first time that this vertex is hit, and we'll take the edge that was crossed when this vertex was hit. So let me just write some definitions. So if we have T in R and X a point in ZD, I'm going to write sigma T of X to be the first time after time T that X is hit by a trajectory of the random interlacements process at time S. So we have these random walk trajectories that arrive in time, and then for every point X, I look at the first, so I define this after time T. So after time T, I look which trajectories have arrived and hit X. So this one hit X. And this was the edge that was used when we visited X for the first time. So I'm going to call this ET of X. So this is the edge used to enter X at time sigma T of X. So it's, is it visible? Yeah. So it's this edge here, ET of X. And now I'm going to define, so let me just highlight that. And now I'm going to define Ft to be the set of all edges ET of X with a reverse orientation for reasons that I will explain in a second over all X in ZT. So for every vertex, we take the first trajectory. So we look at everything after time T. So this is a dynamical way of generating the uniform spanning forest. So for every vertex, so for a time T, for every vertex, we look at the first time after this time T that this vertex was visited by a trajectory. And the edge that was used was ET of X, and we reverse the direction on this edge. And this now gives us an oriented spanning forest, because every vertex has exactly one edge going out of it, because there was only one edge used entering. So by reversing the direction, we get an oriented spanning forest with the property that from every vertex, there is exactly one directed edge emanating from it. Okay, and so what Tom proved, so Hutchcroft in his thesis, is that Ft has the correct distribution for all times T. So it has the distribution of a uniform spanning forest. And actually, the proof of this is not very hard. It's just that it's been a super useful result. The proof goes via another way of thinking of random interlacements and using the Aldous-Broder algorithm in the finite setting. Okay, so now I'm going to define the future of X in Ft as the set of vertices V that have a path starting from X, a directed path from X to V in Ft, and the past of X in Ft is going to be all V, so that there is directed path from V to X in Ft. And the reason why this is the same as before is because we said before that every tree of the uniform spanning forest on ZD is one-ended with probability 1. And here, from every vertex, the future is the unique infinite path that goes to infinity, that emanates from X. So this has to be the unique infinite path from the one-endedness property, and the past is everything that leads to X. So if I just draw it here, so if this is X, oops, this is the past of X, and this is the future. Future and past. And so what we want to understand from before is the size of this component here, the size of the past. And so what we did here actually is we didn't just generate one uniform spanning forest. Instead, we defined a dynamical way of generating this spanning forest. And actually what Tom proved is that this FT is actually a Markov process on the space of spanning forest. And actually this dynamical way of generating the uniform spanning forest works very well when we want to calculate tail probabilities, like what we are interested in. So now I'm going to give you an almost complete proof of the lower bound. So I just want to write here what we want to prove so that we always have it here. So we want to show that the probability that the past of 0 has a path of length n is at least log n to a third divided by n. This is our goal. That's the first. That's the first statement of the theorem, and this is just the lower bound. Okay, so how are we going to do this? So let me just write here that we want the past of 0 in F0. So in order to do this, I'm going to define 3 events, A, B, and C. So let's take some epsilon that I will determine in a little bit. And now I'm going to define the event A to be the event that 0 is hit by a unique trajectory of the random interlacements process in the interval 0 epsilon. So let's suppose 0 is here, and let's say that this is the trajectory W that hits 0 in the interval 0 epsilon. So this part here is the negative part of W, and this is the positive part of W. And it goes in this direction. Okay, so A is just this event. For some epsilon that we'll determine in a little bit, we want 0 to be hit by a unique trajectory of the random interlacements process in this interval. Now, I want to apply the Aldous-Broder algorithm to the positive part of W, to W restricted to 0 infinity. So what does it mean? What is the Aldous-Broder procedure? For every vertex, we take the first time that it was visited. So here we stop there because this vertex here was already visited. Then we continue, we stop there, and then we continue. So if we do this, then it's not hard to show that we're going to obtain an infinite path eta, which is going to have the law of a loop erased random walk in Z4. So what is a loop erased random walk in Z4? You just run a simple random walk path forever in 4 dimensions. It's transient. So it will visit every vertex finitely many times, and then you can erase the loops. Okay, so this is the path eta. And now let's take the first n steps of eta. So because of the procedure of reversing the direction of the edges, this part here is going to contribute to the past of 0. And so since we want 0 to contain a path of length at least n, and we just want a lower bound, I'm just going to give you a strategy for getting this lower bound. So the strategy is the following. If the first n points of eta, so if eta 0n survives the whole Aldous-Broder procedure, then this is going to be in the past of 0. So what do I mean by survives the Aldous-Broder procedure? So first of all, in the event B, I don't want the negative part of W to hit eta 0n. Why? Because we define the Aldous-Broder algorithm we take an edge for every vertex, we take the edge that was crossed the first time when we visited the edge. So since the negative part of W has priority, if it were to hit this part, then it would disconnect eta 0n, and eta 0n would not survive and be in the past. So that's one thing that we don't want to happen. We don't want the negative part of W to intersect the first n steps of eta. And the probability of this is log n to the minus a third. And this is what Lawler proved in the early 90s. So that's one thing we want. We want W and the negative part of W and eta not to intersect. And we also don't want any other trajectory of random interlacements to hit this path here in the interval 0 epsilon. Because if it does, again, if it has appeared before, then it could disconnect it. So then this path would not survive and be in the past. So what we are claiming here is that this part here, eta 0n, is going to be in the past if A, B, and C happen. So, so this gives us a lower bound. So if A and B and C, then 0 contains a path of length n. And now we need to estimate this probability. And remember, we want to prove this lower bound. So the probability of this intersection, we already know the probability of B is 1 over log n to a third. The probability of A, so A is the event that 0 is hit by unique trajectory in 0 epsilon. And so this is up to constants of order epsilon because it's a Poisson process. And then we also want the event C. So we don't want any other trajectory of random interlacements to hit eta 0n in 0 epsilon. And so this is because of the property that I stated earlier, that if you fix a set, so if we fix eta 0n, we don't want any other trajectory of random interlacements to hit it. This is e to the minus epsilon, the capacity of the set. That's the main property I stated earlier. And because eta is random, we have to take an expectation. So we want to prove that this lower bound is of order log to a third over n. And what remains is to set the value of epsilon and to understand the capacity of this loop erased path. And so, okay, let me just write it here. So the capacity of eta 0n has expectation, which is of order log n to the n divided by log n to the 2/3. And so if we were to replace this capacity by its typical value, then we would have to take epsilon to be the inverse of this so that we get rid of the exponential term here. So if we take epsilon to be log n to the 2/3 divided by n, then we are going to get that this is up to constants log n to a third divided by n. And so this proves the lower bound. So as I said before, this is an almost complete proof of the lower bound. I didn't explain why here we can in fact factorize because the events A, B, and C are clearly not completely independent, but that's not hard to justify. And the other thing I didn't explain is why we can replace the capacity by its typical value. But this is not very hard to do. I want to see it. So, and let me just say that one important ingredient here, which is where the power comes from, is the result of Lawler that I stated earlier, which says that if you want to produce n steps of the loop erased random walk, you need to run your simple random walk for n times log n to a third steps. Okay, so this is the proof of the lower bound, and for the upper bound, as I said, I'm not going to go into a lot of detail. So the upper bound is more delicate. Again, we use a similar idea as before. We decompose on whether 0 was hit in 0 epsilon or not, but then we also have to treat both events. And the way we do that is, so if Q of n is the probability that we are interested in, so it's the probability that the path contains a path of length n, then we prove an inductive inequality of this form. So we show that Q of 2n is upper bounded by what we like, log n to the third divided by n, plus a quarter over a quarter times Q of n. And the quarter here is not important. It just needed for the induction, but anything smaller than a half would work. And so in order to prove this inductive inequality, one has to understand quite well the capacity of the loop erased from the MOG. And this is quite tricky to do because it's not a Markovian process. But we're able to use some tools that were used earlier in the work with Asela and Shapira, where there we studied the capacity of a simple random walk. And let me just say that for the lower bound, I said we had to understand the expectation of e to the minus epsilon times the capacity. So in order to understand that, one has to get upper tail estimates for the capacity of the loop erased walk, but these are much easier than lower tails, which are what are needed here, because for upper tails, we can just upper bound them by the same for the capacity of the simple random walk, which is of course larger. And here I just have the theorem that I stated earlier. And I'll stop here.